let's see in this problem how we find the center of gravity by evaluating double integrals. Now try to recall what's the meaning of the center of the gravity. So the center of the gravity is a point. You have the coordinates x bar and y bar. And the mass is balanced around this point. So we use the balance in x direction and y direction over here. In the x direction, we have x minus x bar multiplied by the density over here. This double integral should be equal to 0. That's the balance in the x direction. And in the y direction is similar. If you have a solid in three-dimensional space, then you have another balance equation. But these both double integrals should be equal to 0. This one over here is also equal to 0. And remember, x and y, these are dummy variables. So if you evaluate these double integrals, you are going to end up with x bar and some constants inside. So you can solve x bar from here, and then you solve y bar from over here. Now, we are going to just explain how we set up the double integral, convert it into an iterated integral, and then we leave the evaluation to another tutorial over here. And the second one, the setup is similar, the conversion is also similar, so we will do it simply quickly. But we're going to look at the first one very carefully. So look at this region over here. This region is a triangle, okay? And what are we going to do? According to our setup, we normally do the following thing. We look at where this x variable is bound lower limit and upper limit. And we look at the most left point over here is 0. So x is bound between 0 and b. Okay, that's what we have. Now, when x is moving between 0 and b, in the y direction, the upper and the lower limits are different. If x is between 0 and b over 2, then y goes from this point to this point. Now we can find this equation because this is supposed to be a straight line. So we find that the slope, which is rise over run, and so we have h over b over 2 times x, because this line passes the origin. So that's the equation we have for this line. And on this half of the interval, when x is between b over 2 and b, if we look at the upper limit, or we say the top function over here, it's different because this is straight line, but it's passing b. Because it's a straight line, we can easily find its equation. When x is b, y is supposed to be 0, so you have x minus b factor over here. And then the slope is negative, so we have negative h over b over 2. So we put it over here, negative 2h over b. So that's the equation for this straight line. Now, what it means is that our triangular region R is divided into two subregions, R1 and R2. If we want to convert this double integral over here into iterated integrals, we integrate y first and x second. And that's the setup we need to look at. R1 and R2 together makes up R. R1 means x is between 0 and b over 2. These two are constants, lower and upper limits. Okay. Now, for each fixed x, we try to look at y. Y is between 0 and 2hbx. This way, we describe the entire R1 region. Now, for R2 region, it's similar. You can see x is between lower limit and upper limit. But for each fixed x, y is between 0 and this upper limit over here. We multiplied this out, so we have, for the second term, it's simply plus 2h over here. So that's how we have these two iterated integrals over here integrate with respect to y first, and x second. Okay. There is another way to set up this double integral and convert it into iterated integrals. If we look at this region over here, we say, well, we can actually integrate with respect to x first and y second. How do we do that? You can say, well, look at y. Y is between 0 and h, right? Y is between 0 and h. Now, for each fixed y, your x now is between this point and this point. Now, we have to solve these two equations in terms of y. So from here, because y is equal to 2h over b times x, so x is going to be equal to, we see over here, b over 2h times y. That's the one over here. So let's write it down over here. This is the one we have. If y is equal to 2h over bx, this is the same equation. We can reverse it, and then this is x is equal to b over 2hy. That's the one. And similarly, because y, for the other straight segment of this straight line, y is equal to 2h bx plus 2h. So from here we solve it. X is equal to negative b over 2h, and then we have y minus 2h. And that's the one we have. So we now change the order of these two integrals over here. We first integrate with respect to dx. Then x goes from this point to this point because y is fixed. Y is like the parameter. And then this is on the left-hand side, so this value is smaller and this is bigger. So integrate from lower to the upper limit. And these are the ones we have. And then for each fixed y, we have this integral, and then we integrate from 0 to h. And we only have one integral to do, and that's equal to 0. Now, some of us may say, since we have one integral over here to evaluate, it might be easier. But if we take another look, it doesn't have to be easier than the previous one. The reason, if you look at this one, integrate x minus x bar over here, we have something like 1/2 x minus x bar squared. And we plug in these values for x, and we have quite a lot to calculate. But on the other hand, if we look at this one over here, if we integrate with respect to y first, x minus x bar is simply a constant. And then we have this one multiplied by this value over here, in between over here. So it seems that this calculation over here is a little bit simpler, even though we have to do both of them. Okay. So in the next segment, we are going to try to evaluate these two, because these two integrals involve a lot of parameters, b and h, and then x first over here. But we want to be sure in the final answers to these integrals over here, their values should be only dependent on h and b, not x and y. Alright, x bar and y bar will appear in the integrals as well.